All right, so welcome back. So here we are. We're going to start talking about assignment number 4. So as I mentioned in the first lecture from Module 6, assignment 4 is all about hypothesis testing. So unfortunately, this one's just a straight 100 points. There's no bonus points associated with it. Everything else up at the beginning of it's all about the same. Format the top of it the same way. I want the same thing submitted. Your PDF, your iPi notebook, and your link. So with all those, we come down, the first thing we're going to do is our generic housekeeping, all the libraries that we're going to need. Let's go ahead and get them out of the way to start with. We've got something here where we're importing the random class, and we've set up random with a seed of 42 so that we're going to randomize and we're not going to get the same results every time by putting that seed. So with that said, we've got the pipeline that we need to go through, and we talked about it already to a degree. Start by defining what your default action is. Clearly state what your null hypothesis is. Define your test statistics. Generate many simulated data, as much as you can relative to whatever we're doing. So you're going to simulate data just so that your null hypothesis is true. Compute the test statistics for each simulated data set. The p-value is a fraction of your simulated data set for which each test statistics is at least as extreme as for the real data. So go through, and here we've got some simulated data for June rain amounts and November rain amounts. So it's two separate arrays. And we're going to go through and we're going to feed that data in and plot it. Similar to stuff we've done already. Simple visualization of data. All right. From there, we're going to go through and we're going to kind of do things a little bit different. And we're visualizing it different. The next part is going to be your turn. Got 24 points. 2 tasks, 12 points each. So you're going to create an auxiliary function named permutation sample. And what that's going to do is encapsulate the functionality of lines 4 through 12 above. So we look up here, and we're saying lines 4 through 12, we want to encapsulate them. And we're talking about right here, 4, 5, 6, 7, 8, 9, 10, 11, 12. It's this, all this right here. So you're going to create a function that does this. Essentially, you're outsourcing this to a permutation sample function. All right. So there's 12 points. Write a loop so that you can call that 50 times. Compute their ECDFs and plot them. You're going to get 50 samples and plot them. All right. That's the first part. The second part, we're dealing with test statistics and p-values. So we've got articles here. You can go look to see what's being discussed. And I've got the data that's sitting over in my GitHub. You're going to read it in, get it in the data frame, go do a swarm plot. We see it here. Frog A, frog B, and the associated force for each of them. And then we're going to go through and have an auxiliary function. It's kind of similar to what I told you to do up above. Not saying it's exactly the same, but every little bit helps. Okay. So we're going to test the differences between the two frogs, frog A, frog B. We see, all right, there's differences. Now it's your turn. Write code to compute the probability of getting at least a 0.82 n difference in mean strike force. So when this frog latches out with his tongue, it's hitting at that force, 0.82 newtons. All right. And that the distributions of the strike forces for the two frogs are identical. You'll use the permutation test with the test statistics of the difference in means to test this hypothesis. So create the function diff of means that takes two arrays as parameters, computes the mean values, and returns the difference between them. Seen that. Use the function to compute the difference of the mean impact force, difference of means, perceives force A and force B. Use the function draw perm reps to draw 100,000 permutation replicates, and then compute and print the p-value. Right. Don't panic if the p-value is extremely low. All right. So question 1, and we've got to answer this. It's not a coding thing. How do you describe the result of your hypothesis testing based on the p-value calculated above? And you're going to put your answer in here. It's in your words. Take the results of the work that you did and describe the results. Look and see if you see online where somebody's describing the p-value calculated for hypothesis testing. How do they present the results? How do they describe them? Right. There are ways to do these things, and I want you to see the different ways and decide for yourself based on peer-reviewed journals and based on not, my friend Jimmy did. Find out for yourself what works and what doesn't work, what's normal. All right. And this part we're going to is part 3. We're going to look at the correlation between female literacy and fertility. Okay. And that's throughout the world. So we'll go ahead and work with it. We'll call it the illiteracy rate. Python code below plots fertility versus illiteracy, and it calculates the Pearson correlation coefficient. So we've got an NumPy array called illiteracy. It has illiteracy rate among females is for most nations. And it's got corresponding fertility data. So we see that here. So we're going to pull in the female literacy, DF. We flip it around 100 minus, and that's the illiteracy. Okay. Fertility, that's the fertility. And then we've got our code there. And we see it plotted out. Fertility and the percent of those that are illiterate, 0 to 100. So we come up with a Pearson correlation. And that coefficient's 80. Right, now it's your turn. The observation correlation between female literacy and fertility may just be by chance. The fertility of a given country may actually be totally independent of its illiteracy. You need to test this hypothesis. So to do this, you need to permute the illiteracy, those values, but leave the fertility values fixed. This simulates the hypothesis that they're totally independent of each other. So for each permutation, compute the Pearson correlation coefficient using the Pearson R function that you saw up above. And then you're going to assess how many of your permutation replicates, have a Pearson correlation coefficient greater than the observed one. So you use a for loop, and you're going to draw 100,000 permutation replicates and go through and get the correlation coefficient for each of them. And that's before. Don't panic if your p-value is extremely low. All right. Now, from there, from your code and what you just did, describe. How do you describe the result of your hypothesis test on the p-value calculated above? What'd you see? How do you explain it? Okay. And that's, you're going to put that here. And then the last part of it's your conclusions, and this is what we've done this, been there, seen this before. What have you learned from this assignment? What parts are the most fun, time-consuming, enlightening, and tedious? If you had more time, given your schedule, let's say an additional week to work on this, what would you have done? Okay. That's it. Questions, concerns, reach out. Got the discussions, should be steady going and talking about all the little ins and outs, sharing resources you may have found, GitHub repos, videos, Jupyter notebooks, anything that you found that, hey, I found a great discussion on this, or a great resource where somebody did this. Help others to be able to identify quality resources by sharing your quality resources. Over time, we'd start to understand, oh, this is a great resource, or, yeah, I'm not going to rely on this. The person really didn't understand what they were doing. Okay. So from there, let's jump on and see you in the next video.